And today we're going to talk about shortest paths, dynamic shortest paths, but a different variant, so decremental single source shortest paths. So what is this problem? So we're given, you have already seen a decremental structure yesterday for the all pairs shortest path problem. So here we are given an initial graph G, and I'm going to assume in this talk that it's unweighted. And directed, so we allow it to be directed. You can generalize this to weighted graphs, but I'm not going to do that here. Then we're given also a source vertex, so this is part of the input. And now the goal is to maintain a shortest path tree under edge deletions. So we do edge deletion. And unlike the structure yesterday where we had this limit on how much we could delete from the graph, here we allow any number of edge deletions. So basically all the way down to the empty graph where there are no edges left. And what we're interested in is the total time to maintain these trees over all edge deletions. So there's a classical result by Even and Chiloak. I think it's from 1981 or 82, I'm not sure, but that's right, 81. Which basically solves this problem. It was actually not written explicitly for directed graphs, but it immediately extends to directed graphs. And basically they showed that you can do O of mn total update time. Right, so this is, we're looking at amortized running time. So if you look at how many deletions are there in total, there are m deletions, so the amortized update time is order n, number of vertices. The question is, can we improve this bound here? And actually there are conditional lower bounds, so there's a conditional lower bound of mn. So conditional means that it's not shown to be a lower bound, but if you can break this bound here, you can improve on this, then it will have consequences for many important problems. So it's a bit like if you have an NP-complete problem, then you probably shouldn't look for the polynomial time algorithm, but there might be one, but it would have huge consequences if you could find one. It's the same here. It's not as huge consequences, but still it would. I think many don't expect that you can break this bound here. At least it seems difficult to do it. So what people have done in recent years is to look at the approximate version of it. So we're going to look at, so we consider one plus epsilon approximate single source shortest path. I'm just going to abbreviate it this way here, single source shortest paths. So what does that mean? It means that the data structure should maintain for each vertex u an estimate, let's call it d tilde of s comma u, such that, well, we want, well, let me call it d tilde g S, U. So we never want this to be an underestimate, so we want the actual shortest path to be a lower bound on this estimate. But we don't want this to overestimate the shortest path distance by more than a factor 1 plus epsilon. Okay, so we want to maintain for any such u here. We're not maintaining a tree now. We're just maintaining approximate distances from S to u, satisfying these inequalities. Is this a problem clear? This is what we want to do, and we don't care about worst case bounds. There's actually also a conditional lower bound saying that if you want the best worst case bound you can hope for is order m. So basically running BFS from scratch after each update. So worst case bounds, there's nothing to be done. At least there's a conditional lower bound for that. So we need to look at the amortized setting and also the approximate setting.
But this worst case lower bound isn't for amortized setting also?
Well, the amortized, so there's this amortized, so this would be order n.
But you said that there is a lower bound for worst case of order of m?
M, yeah.
Yes. And this holds for the approximate setting as well?
Yes, approximate, yeah. So today I'm going to talk about a paper that hasn't been published yet, but it's been accepted at SOTA 2020, and it's by me and my PhD student Maximilian Gutenberg. And we have 3 bounds in our paper. So this is a total time to maintain an approximate, to maintain approximate single source shortest path distances. And what this means here, adaptive and oblivious adversary, I will come back to later on. But basically, if you look at, for instance, this bound here, right? So if your graph is dense, so if m is order n squared, then here you have this bound here becomes n to 2.5, right? If you have you start with a dense graph, this is n to 2.5, and even Chirac would give n cubed in that case. So it improves on it significantly. But if you look at this bound for sparse graphs, what do you get? Then you get n squared, and if you look at even Chirac, you also get n squared. So this bound and also this bound, they don't give anything for sparse graphs over even Chirac, and even Chirac is even exact. So there's no approximation in even Chirac. I should also say that even Chirac is deterministic, whereas these bounds are randomized. And that's where this comes in later on. But if you look at this bound here, this actually gives an improvement over even Chirac for sparse graphs. Right, so if you pick m to be order n, then it says n squared here to 7 over 8, that's 7 over 4, n to 7 over 4. So that would be n to 1.75, whereas Chirac would give you n squared. So these are good for dense graphs, and this is good for sparse graphs. And there were some previous bounds that improved even Chirac, but these bounds together basically improve on all the previous bounds. But we're not going to show these bounds because that would take too long. So I'm going to simplify the problem, and we're only going to look at DAGs. You know what DAGs are? Anyone who doesn't know what a DAG is? Directed acyclic graph, so we don't have any cycles. So we will start. I will present these ideas, but only for DAGs, and maybe if we have time, I will sketch how to get these bounds for general graphs. But we're going to get a better bound than these for DAGs. I'm not going to say what the bound is because I want you to do some calculations and figure out the bound later on. But before we look at this problem for DAGs, let's just go through even Chirac, sketch how that algorithm works. So And remember, this is an exact algorithm, so it maintains exact distances. And it actually maintains a shortest path tree, not just distances. So how does it work? So initially, let me draw S, the source, down here. Initially, we just compute a breadth first search tree. Maybe like this. And we can define levels of the tree. So this is level 0, this is level 1, level 2, level 3, and so on. So these are distances from S. Okay, and each vertex, except the source, each vertex reachable from the source has a parent, a unique parent, right? So it's all standard stuff, but there might be more incoming edges than just a parent, right? There could be other edges. So let's look at a general vertex somewhere in the graph. And suppose it has a parent. It will have a parent if it's not the source, and if it's reachable from the source, it will have a parent. That the distance from S to this guy is 4. So we have a path from S. Then the distance from S to this guy is 5. Right. Now there might be other, so maybe I should make this edge sort of fat because this is a parent. There might be other edges. Where could edges come from? Well, they could come from, could be other edges from the same level 4. Could there be edges from level 4? This would not be the path. But there could be edges from the same level. Could also be edges from levels above, even far above. So let's say this is 4, this is 5, and this is maybe 8. So these are distances from S to these guys. Okay. Now there are different ways to implement image log, but there's one elegant way. I think it was described in a paper by Torup and Hensinger. I'm not sure, but it was not described in the original paper, but basically it's quite a nice way to implement this structure. So think of this vertex having all its ingoing edges in a cyclic linked list. Okay, so it doesn't matter how you order them cyclically, but let's say we just order them this way around here, for instance. Okay, as long as this edge is present, and as long as this distance estimate doesn't change, this vertex doesn't need to do anything, right? So when we start deleting edges, what could happen is that the path from this to this can be longer. It can never be shorter, right? Because we only, but it can be longer. But as long as this estimate doesn't change, and as long as this edge is there, this vertex is happy. It knows its distance from S. What could happen now is that there's one case where this edge is deleted. There's one case, and the other case is when this increases. In both cases, this vertex needs to check, do still have a connection from level 4. So it just goes around its cyclic list until it finds another vertex with distance 4 that has an ingoing edge to it. It goes through its ingoing edges in the cyclic order and looks for a vertex at level 4. Maybe it doesn't find one, but in this case it found this one. If it goes cyclically around here, it finds this one. So now, well, suppose that, let's say that this edge was deleted. This vertex now scans around and immediately find this one. Okay. Now suppose that this edge is deleted or this estimate increases. Let's take the other case where this estimate increases, but this edge stays there. When this estimate increases, this vertex communicates to all outgoing edges. I have now increased my distance. So in particular, it will communicate along this edge to this vertex saying, so let's say I'm now at level 5. So So basically what happened is that this went up here at level 5, and it communicates to this vertex, I'm now at level 5. And in that case, it has to do the same thing. It has to try to look for an ingoing at level 4. So it scans around. It continues in the cyclic ordering. So now it comes to this one here. It says, okay, it has level 5. That's not good enough because I want one at level 4. It tries this one. It's still not good enough. Tries this one. It's also not good enough. What can we now say about what should this vertex now do? It's been all around its cyclic list of all ingoing edges. It didn't find one where the starting point of the edge was at level 4. So that means that this should increase its distance from S. So it increases to level 6. I'm not going to move it up, but let's just draw it here. But it might still be that there's no way to be at level 6. Maybe there are no ingoing edges from vertices at level 5. So it scans around again in a cyclic order. So it starts from the scratch here and sees this has level 5. So therefore I will stay at level 6 and I will now get this as my parent. Does it make sense? But also when this guy increased its distance, it has to communicate to all outgoing edges that I'm now at level 6. And then this might propagate. Okay. Basically, whenever we delete an edge, we try to fix the distances from the smallest distance from S and to larger and larger distances. So maybe let's take a bigger example, and I want you to try to work on this for a bit. Let's see. So suppose that this is our initial tree, shortest path tree, right? And now let's say that this edge is deleted. Okay, what happens now? So let me just put the estimates on. So here we have 0, 1, 1, 2, 2, and 3. This edge is deleted. What happens? So I'll give you a bit to think about what's going on here. I mean, I haven't described perfectly, like formally how the algorithm works, but I just want you to get the feel for the algorithm because we're going to build on that. Okay, any suggestions? What is going on here when this edge is deleted? So which vertex are we interested in looking at first? A, yeah. So A now lost its parent edge. Right, so let me delete this one. What should it do now? What should A do? It should scan its cyclic list of ingoing edges, which is now empty, which means it didn't find one that could keep it at level 1. So therefore it goes to level 2. But as it goes to level 2, what does it also do? It has to tell some other vertex something. So it communicates to all outgoing edges. I'm now at level 2. It communicates to C, right? So now A moves up here, right? And it communicated to C that now I'm at level 2. So C lost its parent, like its parent increased, so now it tries to look for an ingoing edge from a vertex at level what? Well, it tries to find an ingoing edge from a level 1, right? It doesn't know that there is no, we can see that there is no ingoing edge from a, but there could have been an edge from B to C, so it has to scan around. Is there an ingoing edge from a vertex at level 1? And it has a cyclic ordering. It starts somewhere, so maybe it starts at A. No, it's at level 2. That's not good enough. Tries this one. It's also level 2. It's not good enough. Tries this. Well, no, sorry, this was an outgoing edge. So it didn't find one at level 1 that connected to it. What does that mean? It means that it cannot be at level 2. It has to increase. And we process vertices from smallest distance to largest distance. So when we process C, we also process A, and the same thing happens. It will also increase to level 3. So maybe I should draw it here. So now E, C, and A are at level 3. And D is still at level 2. B is here. And S is down here. Oops. Okay, and now let me draw the last edges. So there's an edge going here. There's an edge going to C. And there's an edge going from C to E. And there's an edge going from A to C. Did I draw them all correctly? Okay. So now we're done at level 2, so now we look at level 3. And these, so let's see, so these 3 vertices now lost their parent, they don't have a parent yet. So we process them in some order. Let's say we take A first. It looks for an ingoing edge at level 2, from a vertex level 2, it didn't find one. So it will have to increase to level 4. This C will also go in through all its ingoing edges in a cyclic order, and it actually finds that there's an ingoing edge at level 2 here from D, so it will connect to that one. It can stay at level 3 now. And the same with E, it will also scan and it will find this one here. And A will continue, it will basically never find any ingoing, like it doesn't have any ingoing edges, so it will just continue. I mean, in principle it would continue to infinity, but where could we actually stop processing a vertex? At what level could we stop processing it? At level, so if it reaches level, I thought I heard the right answer, but level n, someone said? Yes, so if a vertex reaches level n, then we know that there cannot be a shortest path from S to that vertex, because it's a unit weight graph, and the longest distance you can, finite distance you can have is n minus 1. So now the question is, why do we get this O of mn total update time? Do you see that? I'll give you a moment to think about why is this algorithm running in O of mn time? So any suggestions? The way we described it here, do you see how we get an O of mn time bound? Total time bound? So whenever a vertex increases its distance, it scans its neighborhood, right? And so when it loses a parent, it scans its neighborhood and tries to look for one. But the way we did it was because we had this cyclic ordering. So we had a parent here, and when this parent, maybe this edge was deleted or this estimate increased, this vertex would continue in its cyclic ordering and try to look for an ingoing edge from the same level, right? Once it has scanned all its ingoing edges once, what do we know? And it starts over again. What do we know about its estimate? What has happened to it? Like when it loses this edge here, it might find the very next one in its cyclic ordering might be a good edge, so it just connects to that one. Maybe then it loses that edge. It continues scanning around. It finds another good edge at the same level, so it can keep its distance from S. But once it's scanned all the way around and starts over again, what must have happened? It must have increased its estimate by at least one, right? By exactly one, the way we implemented it. So every time it increases its estimate, it has scanned all its ingoing edges at most once. Each of its ingoing edges at most once. And also it needs to communicate out to outgoing edges that now I have increased, but that also just happens one per level increase. So basically every vertex pays its degree in total how many times over the course of the algorithm? Can you give a bound on that? Pays its in and out degree how many times? N times, right? So, and if you sum up the degrees of all vertices, both in and outgoing, you get order m, right? So therefore you get order m n total update time. Was that clear? So it's a really nice algorithm. So let's now build on this and try to get something faster for DAGs. But now we allow approximation. So I want to define, I want to give edges artificial weights. And the way you should think of these weights is that they are flexible. They can you can stretch and shrink edges or their weights. So initially, so before the first edge deletion, let's say during pre-processing, each edge UV is assigned a level, and I will not describe how these levels are assigned yet, that we'll come back to that later on. But let's call it L of U, V. And this level here is a natural number. It's a bit similar to the first lecture on dynamic connectivity. Okay. Now we define the weight I mean, we are looking at an unweighted graph, but we assign these artificial weights. Let's call it W, U, V. So let's define it as follows. And this will look a bit weird at first, so let's look at it in a moment. I will use some notation that I will introduce. Sorry, this should be. Let me just define what I mean by this. So I'm writing this notation here, floor of x with subscript I. Oh, sorry, this should be, well, sorry, where I is the level of u comma v. Yeah, no, let me write it this way. So where x seal with I is the smallest power of 2 strictly greater than x. Okay, so this is quite weird because I'm defining the weight of an edge, but the right-hand side of the definition also depends on the weight function. But notice the right-hand side doesn't depend on v, it only depends on u. So suppose
shouldn't be there some I in the definition of this string I?
So this is I. I is the level of.
Yeah, but where seal x of I?
Oh, sorry. No. This is smallest. No. I was too quick there. So it's the smallest multiple of 2 to the I. Thank you. That's what I meant. So I think we should take an example. So suppose so basically this here defines the shortest path distance from S to U with respect to this weight function. Okay? Suppose this is well defined, even if we're trying to define the weight of U comma V. Suppose we already have defined this distance here, and therefore also this distance here. So let's take a concrete example. Suppose that, let me draw it slightly bigger.
So is it for graphs only now?
This is for general graphs, but we're going to look at DAGs later on. But this definition works even if it's if it has cycles. So suppose that this edge, the level of this edge here is 4, and this distance here is 13. Distance from S to U is 13. What weight would you give this? What weight should this edge have? If you look at the definition up here, so I'm saying that this value here is 13. What should the weight of this edge be in this example? So what is this value here? You need to look at the smallest multiple of what? 16? Strictly greater than 13. That's 16. So this is 16, this is 13, so this should have weight 3, right? Does that make sense? That ensures that the distance from S to V is now, like if this was the shortest path, if the shortest path went through this edge here, that means that this is now, this distance from S to this vertex is divisible by 16. Like if we changed this to 12, if this was only 12, what would happen here? It will increase to 4. The distance didn't change to V through this vertex U. Was that clear? And you can show that this is well defined, because basically what you can do is you can start by looking at S. It has distance 0, clearly, to itself. And now the weight of all outgoing edges from S are now well defined with respect to this function. Because this will now be 0, and this will be the smallest multiple of 2 to the I, strictly greater than 0. So this defines the weights of these edges, and now you can look at outgoing edges of these, and they will also be well defined. So basically you can think of defining this weight function by running Dijkstra starting from S, and you this will define the weights of these outgoing edges, and you keep running Dijkstra and you will define weights as you go along. Because whenever you come to a new edge, U, V, you already found this distance here, so the weight is uniquely defined. But you can see what happens now. We are in the decremental setting, so distances will increase over time. And what you can see here, what happens is that when U increases its distance from S, it doesn't need to communicate anything to V before what? When does it need to communicate something? In this example here. When it increases to, let's say it increases to 13, does it need to tell V anything? No, because V, so suppose that this was the shortest path. It goes like this here. It increases to 13. It will not compute the new weight of this edge. It happens implicitly. So this will just implicitly increase to 3. But U knows that if this is a level, all the level I edges here, where I is 4, I don't need to worry about, I don't need to communicate anything along these edges before my distance increases to what? 16, or something divisible by 2 to the I. Whenever the distance from S to U is divisible by 2 to the I, divisible by 16 in this example, then it has to tell something to its outgoing level I edges. But it could have level 3 edges also. So let's say this is a level 4 edge, but U might also have a level 3 edge going out from it. When does it need to communicate something to its outgoing level 3 edges? When its distance from S is divisible by 8, right? And level 0 edges, they basically, every time U increases, it has to tell its outgoing level 0 edges, I have increased. So this is like normal even Chilliwack. But if you have high level edges, U very rarely has to do any work. Okay, so yes. So basically what is going to happen is that as U increases, say V increases, this edge is shrinking all the way down to when it has weight 0, then it springs back and gets what weight again. So U increases to 50, then this weight is 1. And then when U increases one more time, then this edge will be squeezed down to weight 0, which is not allowed, so it will jump back again and have what weight. So now, if it increases to 16, what weight will this now have? Well, any suggestions? 15. So this weight will be 15 now. 16, yeah. So that means that the distance to V through this vertex suddenly jumps to 32. So it just jumps from 16 to 32 immediately. But V still has to look for other ingoing edges as usual. Maybe it can stay at level 16. But basically, it will jump with multiples of 2 to the I when it uses these level I edges. Okay. So basically, let's see. So each vertex only scans its outgoing level I edges once its distance from S is divisible by 2 to the I. Okay, and by the same argument, so every ingoing edge is only, to a vertex is only accessed every 2 to the I levels, basically. So what running time will we get now? So let's look at the running time. So any questions so far, by the way?
Is this still an exact algorithm?
So that's a good question. Is this still an exact algorithm? Well, it's an exact algorithm with respect to this weight function, this weird weight function. It maintains exact distances, but not with respect to the original unit weights, but with respect to this weight function. But you get approximately, if you want to use this to, you only get an approximation to the true distances, because edges can be more expensive now. But it can never be cheaper than the original distances, because these weights can never be smaller than 1, right? They will also always be 1 or larger. So what is the running time? So let's look at this. So by the way, I should say, maybe this is an important point to mention. Let's just go back to eventual log briefly. Suppose that you, because we're going to need this in a moment, suppose you only want to maintain distances up to level D with eventual log. So suppose that you don't care about distances up to level n-1, just to level D. What will be the running time of eventual log? Yeah, O of D times M. It's the same argument, right? For every level, a vertex pays its degree, and now there are only D levels to consider. So we can also do this for this modified eventual log. So let's see what is the running time up to distance D, and here by distance I mean distance with respect to the weight, right? Up to weighted distance D. And here it might be more convenient we need to somehow, because edges have different levels, so we need to look at each edge individually to see how much it pays. So let's write this as a sum over all the edges. How much does, like for normal eventual log, each edge is paying D in total, right? You can think of every edge being scanned only order D times. So every edge here, every of the M edges pays D cost. What if you look at this modified eventual log, what does an edge E pay? How much does it pay? So let's write something that is not correct. So this would be normal eventual log, because there are D levels and it would pay So it will pay d times. But what should I change this to? So remember, when you look at this edge here, right? If it had level 4, then it would, the maximum weight would be 16. Then it would could shrink all the way to 0, and then it would jump back to have weight 16 again. But when it shrinks from weight 16 to 15, does it need to be scanned? Right? So let's just take this again. So suppose that this is 16, then this is 32. When this, so this weight is now 16. Now this estimate increases. Do we need to scan this edge here? I mean, as I said, we implicitly reduce the weight of this edge. We don't need to do it explicitly. So we don't need to scan this edge, right? And when it increases to 18, we still don't need to scan it. We only need to scan it when this becomes 32. Then it has to be scanned and say, now I go back to have weight 16 and I need to communicate that to V. So can you now see what would be the contribution of this edge to the total cost if you have up to distance d?
D divided by 2 to the power of 11.
Yeah, exactly. D divided by 2 to the power of the level of E. Okay. And then there's a special case because this value here could be less than 1, but you still need to look at every edge at least once in the graph. So there will be, I mean, you also need constant time. So let me write it like this. So you have m plus this sum here. It's just a technicality. But does this make sense? Like if the level of the edge was 4, then this denominator is 16, and the total distance is d, but only every 16 levels of u here, it will be scanned. So therefore we get this running time bound. Okay. I think just because it's a long lecture, I think we'll just take 5-minute break and then we'll continue. Okay, so let's continue. So as I mentioned, we're going to look at it for x. So now we're going to look at decremental 1 plus epsilon approximate single source shortest paths in DAGs. And we'll maintain distances, but you can also use it to maintain paths. Let's just look at maintaining approximate distances. And think of, epsilon, it doesn't have to be constant, but you might want to think of it as some small constant, okay? Yes, so let's see. So we have a pre-processing step. Actually, no. Let me say something first. So let d be a power of 2 between 1 and say n divided by 2. Let's just say n, doesn't matter. So we will present a data structure. So 1 plus epsilon approximate data structure maintaining distance estimates let's call it d tilde S comma U, this is for all U, such that this is never allowed to be an underestimate. And if the true distance from S to U is in this range here, this half open interval, then it should not overestimate by more than 1 plus epsilon factor. Again, this is for all U. So why is this enough to do this? I mean, if we don't care about log factors, why is this fine? If you have such a structure, if you can show a good bound for this structure, how could you get one for arbitrary distances? So you would have a logarithmic number of structures, right, for each choice of D. Each of them will never underestimate the true distance. And yeah, they have this property as well, that if the true distance is in the right range, then that structure for that range gives a good estimate. How would you, so let's say we maintain all these logarithmic number of structures, how would you then get an estimate so that no matter what the true distance is, you always get something that is at least as large as the true distance and at most 1 plus epsilon times the true distance? You see how to do that? What if you just, whenever you want a distance, you just ask each structure their estimate and then you take the minimum of them? Right? If you take the minimum of these estimates over all structures for all these ranges here, that minimum will not be lower than the true distance, right? And we know that when you have a U here, the distance from S to U must be in some range here. I mean, it could also be infinite, but in that case it's fine as well. But there must be, otherwise there must be some range here where the true distance is in, and that structure will give a good estimate, so the minimum over all of them would also give a good estimate. So is it clear that this is enough? So we just focus on one such range, and we will look at that. Okay, so there's a pre-processing step, as I mentioned. So compute topological order, topologically sorted order of the DAG we have. Let's call it G, let's call it DAG G, E. So you all know what a topologically sorted order is, and you know that a DAG has such an ordering. It can also be found in linear time, so this will not be a bottleneck in the running time. I haven't mentioned what the running time is yet, but we cannot beat linear, so this is fine. So that means that we now have an ordering of the vertices. Let me just draw it here, where all the edges go left to right, right? So and there can be more edges like this. Okay, so this is what we do in the pre-processing, and now we want to assign weights to these edges, like this kind of weight up here. Well, actually we want to assign levels to the edges, and the levels will define the weights. Now basically the idea is that let's say S is here. The idea is that if you have an edge that goes far ahead in the topological ordering, that cannot, in a shortest path from S to a vertex U, there cannot be many edges that go forward by a lot, right? You can only move, in the shortest path from S to some vertex U, you can only move from left to right. So, but there are only n vertices in total, so you cannot jump a large amount too many times. Therefore, we want to give edges that jump far, we want to give them high weight or high level. Because it's fine to make them expensive because there cannot be many of them. So let's just define, so let tau of U be the topological order number, let's call it that. So let's say that this vertex has number 1, tau of S is equal to 1, let's say, and this has 2, 3, 4, and so on. So let tau of U be the, let's call it the rank of U in the topological order. So tau of S will be 1, and so on. So that was a pre-processing. Well, no, so we also need to define the levels. So let me just define. So for an edge, U comma V, so I should have defined this earlier. Let me write it up here because this is not part of the pre-processing. So let me just define something here. So let W max of U comma V. So once we have defined the level of an edge, W max is equal to 2 to the I. This is basically the largest weight that this edge can have. And it has if it has level 4, then the largest weight this edge can have is 16. So that's just the definition. Okay. So what I want now is, we'll see this in a moment, but what we want is, we want to choose L of U comma V such that W max of U comma V will be at most 1, we need at least weight 1, plus tau of V minus tau of U divided by N and multiplied by epsilon B. This is not clear yet why we want that, but suppose we chose the levels such that the maximum weight that this edge can have, so basically 2 to that level, is at most this value here, this weight here. Okay, so suppose we chose them. I haven't explained exactly how we choose them, but just suppose that we chose the level such that this holds for all edges. Okay, so by the way, this topological order here, when we start deleting edges, will it still be a topological order for the graph? Clearly, right? Because we're not adding edges, so this will still. So we keep this topological order throughout the sequence of deletions. So now let's consider some point in the algorithm where we have deleted some edges, and we look at the current shortest path. So these levels are defined in the pre-processing, but I will describe exactly how it's done. But suppose we have defined the levels. So consider a shortest path with respect to unit weights So this is a true shortest path. So I'm ignoring the weight function here. So consider an actual shortest path from S to some vertex U, where let's call it P. Where the length of this path, so where, let me just write it this way, it's the same as, let me write it this way, which is the same as distance from S to U is in this range we're interested in, right? So we were only caring about these distances in this range. Okay. What is, now we want to, so suppose we chose the level so that we have this inequality. We want to show that the approximate distance that this modified eventual arc that we described with these flexible edges, the approximate distance that maintains is a 1 plus epsilon approximation of the length of P. Then, let's see. This is our estimated distance, right? This is with respect to this weight function. What can we say about that? We can upper bound it by summing over all edges u comma v in P of the maximum weight that this edge can have. Okay, and then we use this inequality here. So this is at most 1 plus tau of v minus tau of u divided by n multiplied by epsilon d. Right? Now what does this sum to? Well, if we take all these 1 unit contributions, what do they sum to? They sum to length of P. So this is, so let me write it, less than or equal to the length of P plus, let's move epsilon d and n outside. Tau of v okay. Now what can we say about this sum here? The sum of all these differences in topological, these ranks. You have a... So here we have 7 vertices, right? And maybe we look at, let me draw a path here. Suppose this is our path that we're looking at. I don't know if it's the shortest path in this drawing, but let's say it's this one. So we want to look at what do these sum up to at most. So these are basically the difference in ranks of the endpoints of the edges. So this will be 3 plus 2 plus 1. Right? So can we now give a bound on this sum here in general? Any suggestions? N is a good bound, right? So this is at most Can you all see down here, or maybe it's too low? I think I can just write here maybe. So P, and so this is summing to at most n, and that cancels out with this n. So this is epsilon d, right? And what can we say about epsilon d? What can we say about d in compared to the length of p? Right, we assumed that the length of p was in this range here. So this is less than or equal to the length of p plus epsilon. And that's a 1 plus epsilon approximation, right? So this is equal to 1 plus epsilon times the true distance from S to U. Hope you can see that. So, any questions for that? So if we could choose the level such that this holds, then we get a good approximation. So now we need to choose the level so that this holds. And we also need to, we could of course just choose all the levels to be 0, then this would hold, because then the weight would be at most, the W max would be 1, and that would be at most 1 plus something. So we could just choose all the levels to be 1, then we're fine. But that would just be, we could choose all the levels to be 0, then we would get actually an exact algorithm that's basically Even-Shulak, normal Even-Shulak. So we don't want them to be chosen too small. We want to choose them as large as possible so that this holds, right? Because then we get as a good running time as possible. So in the pre-processing step, for each edge u comma v, pick W max of u comma v to be the largest power of 2 value at most this here. I just chose that W max has to be a power of 2. I'll just choose it as large as possible so that this inequality holds. Then clearly this works, right? And now the only thing is the running time analysis. So what running time will we get with these choices? Now we want to use this result up here, right? So I want you to work on that, but let's just do the first few calculations, and then you can try to finish them after the break. So, running time. So we want to use this, so we can just write up the running time already as expressed exactly this way. So the running time is O of m plus, so the question is, what should we choose d to be? We shouldn't actually choose this d. Remember this, but this weighted distance, right? This is a running time when you maintain distances up to value d with respect to the weight function w. So what choice would you use instead of d there? to make sure that we catch all the distances we want. In like we had this, or I erased it, but we had this range from d to 2d. We wanted to approximate distances in that range, in this range here. So what would you choose the distance up there to be instead of d? So we assume that the true distance we care about is at most, or actually less than 2d, right? If the distance is larger than d, we don't need to worry about it. But how large can the approximate distance be? We know now that we get a 1 plus epsilon approximation. So what is the largest approximate distance we need to worry about here?
2D.
2d. So if the approximate distance is larger than 2d, are we then fine? And why? Could it be that the true distance was slightly less than 2d, but the approximate distance, because there's a 1 plus epsilon factor, is larger than 2d? So we want to maintain it up to approximate distance 2d times 1 plus epsilon. Is that clear? Because if the approximate distance is larger than 2d times 1 plus epsilon, then the actual distance must be larger than 2d. Okay? So instead of d up there, we will use this bound. So we sum over E in our edge set E of 2d times 1 plus epsilon, so this will not matter for the asymptotics, but I will write it anyway, divided by 2 to the level of E. What is, maybe I should let me write it as u comma v, because we will be easier to see. So we sum over all edges u comma v in E, and then I have level of the edge u comma v here. What is this 2 to the level of u comma v equal to? Do we have something that we can replace? That was W max, right? That was the maximum weight. So this is, and now I'll just get rid of 2 and 1 plus epsilon. Let's assume that epsilon is a constant, at most a constant. So this just disappears in the O. So we get O of m plus, we can move d outside the sum. And then we have 1 divided by W max of u comma v. All right. And now shows it to be the largest power of 2, which has this restriction here. Right. So what does that mean? It means that, so we want to say that this is a large value. This denominator is large. It's basically roughly this value here, right? It's at most a factor 2 smaller than this. It's at least half of this value here. Is that clear? But then you can make it even. You can make it even. If you remove this plus 1 here, you get something that is smaller here. That means when you divide it here, you get something larger. So if we just care about an upper bound, we can just replace this by O of m plus d times the sum of 1 divided by this value here, basically. So 1 divided by tau of, maybe I should make a parenthesis here, tau of v minus tau of u divided by n and times epsilon d. And then we get like this. Okay. See that here we're actually dividing by d, here we're multiplying by d. And this n goes up here, right? So we get m plus these cancel out, we get 1 over epsilon here, and we get an n outside. I think that should be correct. Otherwise, let me know. U, v, e of 1 divided by tau of v minus tau of u. Okay. Now and then afterwards, you try to finish these calculations and see what bound do we get, what running time bound do we get. So let's take the break now. No suggestions? Or any idea what we could do with this? Could we change it somehow so it's easier to calculate? So okay, let me do one more step and then you can try to think about it again. So instead of summing over all edges, just having one sum, let's make a double sum. So let's sum over all vertices u in V, and then sum over all edges u comma v, all edges outgoing from u basically of the same. So this is of course the same sum, same value. So now do you see anything nice here that happens? So for a fixed u, what can we say about this here? So now tau of u is fixed, right? So can we give some bound on this sum here?
N minus 1?
Sorry?
N minus 1?
So this whole thing here is summing to n minus 1? This inner sum, you mean?
For 1.
For 1u? If this sums to n minus 1, then you need to multiply that by another n here, and another n here. That would be n cubed over epsilon. That would be bad, right? So we want a better bound.
Log n.
Yeah, sorry? Log n, yeah. Why log n?
Sum of 1 per I.
Yeah. So this is, so if you look at it, so now we basically we're looking at this topological ordering, right? And u, the current u we are looking at is somewhere. And now we're basically looking at all outgoing edges from u. And we're looking at these fractions here. There can be at most one edge from u to this vertex. It's a simple graph, right? So there can be at most one edge here. So the largest contribution, the largest that this sum can be, is that if every vertex to the right of u is connected from u, right? And these differences here are just the difference in rank here. So this will be, this denominator will be 1 here, 2, 3. So this is just O of M plus, let me write it over here if I need more space. Of basically the sum, we just want an upper bound, so let's say we sum from 1 to n of 1 over I. Right? What is this summing to? As you said, it's the nth harmonic number, which is theta of log n. So this is O of m plus n over epsilon, and then you get log n, and you have n terms, right? So that's n log n. So we get, and basically this here will dominate m here, because this is more than n squared. So I was just out of space, so let's continue over here. This is just n squared log n over epsilon. But that was for one of the structures. Remember, we had logarithmic number of structures for each power d, a power of 2d. So the final bound over all structures will just be this times log n, so we get an extra log factor. So the bound that we get is basically quadratic in n. So this is optimal for dense graphs, basically, dense DAGs. So this is only for DAGs. Is that clear? Okay. But I wrote up, in the beginning I wrote up these bounds here. They were for general graphs. So it's not clear yet how can we use this approach? Well, how can we generalize it from DAGs to general graphs? I will not have time to go through all the details, but I'll just give you the intuition. So it will be high level. I'll just spend a few minutes on it. How can you turn a general graph into a DAG? What would be a natural thing to do? Like, can you contract? What would you contract to get a directed acyclic graph?
Strongly connected.
Yeah, strong. If you contract all the strongly connected components, you get a DAG, right? So the first idea we could try is just, we have an algorithm for DAGs, we want an algorithm for general graphs, we just take our general graph and contract all the strongly connected components, and then we run this algorithm on it. Does that, I mean, there are several problems, because maybe when you start deleting edges, a strongly connected component falls apart, but let's say we could handle that. Is there another problem just contracting all these strongly connected components?
Different results for different nodes.
Different results for different nodes, like?
Components, like 2 nodes that have different distance.
Yes, so when we contract strongly connected components, we're basically saying that all the vertices in that strongly connected component have the same distance from the source, which is not in general true. And also, let's say we have S here, and we have a shortest path in this contracted graph. So this vertex here could be a huge strongly connected component, could have a large path inside it. But now we're just saying it costs 0 to go through this one. So this clearly doesn't give good approximate distances. Like if the whole graph was strongly connected, we would just contract it to one vertex. We will lose all information. So the idea is to get these results over here, is that if you look at a strongly connected component, let me draw it like this. So this is a strongly connected component. You look at the diameter of it, so basically the longest, shortest path you have in it. If this diameter is small, then it should be fine to contract the strongly connected component. So the idea is to say, if you have a strongly connected component that has small diameter compared to how many vertices it contains, then you can contract it. then you might get some, you still have a problem because you still underestimate distances. Let's say that I have my distance from S to T, and maybe I contract strongly connected components that have diameter 2. Maybe all of these have diameter 2, and then we're basically shrinking the distance from S to T by factor 2 maybe. So that would not work either. But the intuition is that the more vertices a strongly connected component contains, the more diameter we can allow it to have. Do you see why that is the case? If we look at SSCs that have, let's say, vertex size larger than or equal to, let's say, n-half. How many, so if you look at a shortest path from a vertex, from the source to a vertex T, and now we just look at SSCs of vertex size at least n-half. How many of them can there be in such a path? At most. But yeah, so there could be, I guess there could be 2 if they had exactly n-half size, right? But there's only 2 of them. And that means that you can actually allow them to have quite big diameter, because they only contribute, there can only be 2 of them that give an error in the distance. I mean, this is very high level because it's too technical to go into details, but the idea of the algorithm now is that if a strongly connected component has too large diameter, then we want to split it up. So basically you want to cut it somehow so that it falls apart into smaller strongly connected components. So you remove some vertices, and then this strongly connected component falls apart into smaller bits. And if those have too large diameter compared to their size, you recursively split them up, and so on. And what you can show is that if an SSC has large, actually if any graph has large diameter, then you can find a small such cut. So there are not too many vertices in this cut here compared to the 2 sides here. And now if you look at the topological ordering after you contracted your SSCs, you will have edges going forward like a normal DAG, but now you also have these problematic vertices that you took out. So if you add those in again, they can actually send you backwards, so you have back edges now. But because there are only few of these special vertices here, you cannot have too many you cannot be sent back too many times in a shortest path. And therefore you can still use this weighting, these artificial weights but you don't get n squared, you get these weaker bounds here. Well, that's sort of the high level idea. I don't know if it made any sense, but I won't have time to go into the details. But now the question is, what do these words mean here? So we have this bound for an adaptive adversary, and then we have these 2 bounds for oblivious adversaries. So I thought I would just talk about that now. So this was basically the remaining slides from the first lecture that I didn't have time to go through. So these bounds here, they are all randomized. So the algorithm you have seen for DAGs is deterministic, but once you do this, if you want to do this trick with the strongly connected efficiently, you need to use randomization. And that's why we have these this notion of adversaries. So let's talk about that. So for several, do I have this switch? No, I was thinking of switching slides, but I can also just do it manually. I mean, that's fine. So for several graph problems, including dynamic graph problems, the fastest known we have are randomized. And there are 2 types of algorithms or data structures. I think we already talked about this, Las Vegas and Monte Carlo. So just in case you don't know what that means, so Las Vegas algorithm, it always gives the correct solution, but time and space are random. And Monte Carlo algorithm may give the incorrect solution like the algorithm we saw yesterday, but typically you define it to say that the time and space are not random. There's also a definition where you allow Monte Carlo algorithms to both give incorrect solutions and have random time and space. But usually you can avoid this being random by just saying that if I spend too much time, then I just stop and return anything. Then I will make a mistake, but I'll make a mistake, but I'm allowed to do that. So the problem with dynamic graph algorithms is that you have an interaction with a user, right? Normally in a static graph problem you have a problem instance, you get some input, and then you can use randomization, you get some output. And there's no user that can screw. But in a dynamic setting, you have an online sequence of updates and queries from the user. And now the problem is that this dynamic graph algorithm or data structure outputs something to the user. For instance, an approximate distance or something. And if that information somehow reveals what random bits the data structure is using or the algorithm is using, then the user might be really evil and try to make the algorithm run slow. And therefore, you need to be really careful when you design randomized dynamic graph algorithms, because you want to avoid having the user screw up your analysis, because like, if the user knows what your random bits are, then that user can choose a really bad sequence. Like it starts updates and queries, and then it learns maybe, your random bits are like this. Now I will give you a really nasty sequence for the rest of the sequence of updates. So such an algorithm either needs to somehow hide its random bits from the user, or assume that the user is not adaptive, and I will describe that in a moment what that means. But it basically means that the user is not evil. It cannot screw things. It won't screw things up. But let's look at a concrete example. We have already seen this problem. So approximate shortest path. So suppose we have some algorithm. Let's say it's randomized, and it should support updates, insertion, deletion of a single edge. We can also just look at deletions only if you want. But this is just we don't need to worry about the details, just some problem. And then there are some queries, like we have seen, that you can ask, given two vertices u and v, maybe you want to say that u is just the source, if it's single source. Then the user can ask the data structure, give me an estimate of the true distance from u to v in the current graph. And suppose that we have seen 1 plus epsilon today, but let's just call it delta. So this is the error. So the approximate distance is never an underestimate, and it can only it cannot overestimate the true distance by more than a factor delta. So here delta is at least 1, of course. Now, the only thing that, if the user can go and see the random bits directly in the memory, then we cannot hide it. But suppose that the user can the only information it gets from the data structure are these approximate distances here. Now it's not clear, but maybe this could actually reveal something about the bits. Like if the user is really clever, like you need to think of some kind of von Neumann guy who is really smart, or just some algorithm that is really clever and can figure out that, well, if I did 3 updates, and in the 4th operation I do a query between 2 specific vertices, and that approximate distance is maybe very close to delta, then I know that the 10th and the 15th random bits are 1. Like this error here, this flexibility here can reveal potentially something about the random bits. So we in dynamic graph algorithms, we look at 2 types of adversaries typically. There's another one, but we'll just focus on these. So an oblivious adversary, basically you can think of, there are 2 ways to think of it. Either the entire sequence of updates and queries is fixed in advance. So before the first update and query, then the user has to decide exactly what queries and updates to do. And then it cannot adapt to the outputs from the data structure so in the online setting. So you can think of it either as the sequence of updates being fixed in advance, or if you don't want to do that, you can say that, well, I don't need to fix my sequence in advance, but when I get an answer to a query, I cannot use that information to decide what my later updates and queries are. I have to just ignore that information. So if that's the case, that's a friendly user, right? It's Oblivious Adversary. It cannot screw up anything. But an adaptive adversary is basically the opposite. So here, this user is allowed to choose subsequent updates and queries based on the information revealed through the information from the queries. And this is maybe a more realistic setting, because usually maybe, let's say you want to maintain some communication network, you query, are these two vertices well connected? And the algorithm says, no, they're not well connected. Maybe you want to do some updates to connect these two users back. But then you're an adaptive adversary, right? Because now you're doing your updates to your graph based on the information that the data structure gave you. Is that clear? You see that there's an issue here that you need to take care of. And basically the bounds over here are, for those two types of users. So this bound here is weaker than this bound, but it works against an adaptive adversary. And basically, so the problem here is that the distances we return here are 1 plus epsilon, approximate. So we have this problem from the previous slide, that this estimated distance might reveal something about our random bits. What about the problem we saw yesterday? Is that a problem with the, could there be an adaptive adversary that could screw things up there? The problem we looked at yesterday, all pairs shortest paths. So what variant did we look at yesterday? It was fully dynamic, all pair shortest paths. Was it approximate? It was exact distance, right? So it was maintaining the exact distance matrix. What can we say about this problem in terms of the types of adversaries that there are? Problem for that? So the problem here is that the problem on the previous slide was that this estimate could reveal something about the random bits. But if you look at the problem we looked at yesterday, there was exact distances. Can the output from each update reveal anything about the random bits? No, it's just there's a slight detail that it's a Monte Carlo algorithm, so sometimes it might give the wrong output. But in that case, we're screwed anyway. The algorithm doesn't need to do anything correctly. But let's look at up until the point where the algorithm might fail, because that happens with very low probability. The sequence of updates up until the point where the algorithm might fail, it just outputs the true distance matrix. And there's no information about random bits there, right? Even a deterministic algorithm would output exactly the same thing. So in the exact setting, an adversary cannot learn anything about the random bits. But there's actually a slight, if the adversary is really clever, it could actually still learn something about the random bits. Do you see some way to for the adversary to do that, even if we look at the exact setting? So each time, after each update, the algorithm outputs the distance matrix, n by n distance matrix, true distance matrix. Could an adversary still learn something about the random bits?
You could measure the time.
Yeah, it could measure the time, the running time, because it might be that if an update takes a certain amount of time, then it's because the random bits are in this particular way. Right. Could we, so what we looked at yesterday was worst case running time, right? Can we somehow hide that information about time to the adversary in the worst case setting? Like we had an upper bound, we had this so tilde of n to 2 plus 2/3. That was the bound we showed, right? But now, as you said, this is just an upper bound. So if you look at, let's say we look at the update time on the y-axis and the update number on the x-axis. Then we know that there's some upper bound, this upper bound on the running time, but the actual running time might look like this, right? There's some noise here. Some updates are faster than others, but all of them stay below this threshold we have shown here. But this curve here might reveal information about the random bits. Do you see a way to deal with that? I'll give you a short time to think about it. Any suggestions? What can we deal with this issue? If the adversary has a clock and allowed to measure the time for each update and then learn all about our random bits, or at least so much that our analysis is screwed up, what could we do here in this case?
We wait each time.
Yeah, you would wait each time. How much would you wait? How long? Yeah, so what you can do is, let's say that in the first update we spend this much time here, then we're finished, but instead of returning to the user, we just busy wait, we do busy, just a loop, until we spend exactly this time here. Because the algorithm can also measure how much time it has spent so far. So it knows how long to wait. In the next update, maybe it was slightly faster, but then we just wait slightly longer, and now basically the time for each update will match exactly this upper bound curve. And then this information is hidden as well. What about if you have an amortized data structure or algorithm? Could we use this trick as well? Then it's not clear, right? Because there might be some updates that are really long and some that are really short. We cannot make each of them take the same amount of time, because then each of them would take as long as the longest one, which could be very large. So that's a problem for amortized data structures. But for worst case, you can do this trick here. Right, so there are two ways around this problem. Either you just say, we assume an oblivious adversary, then it's a weaker result that you show, but you deal with this issue that I showed on the previous slide. But it significantly limits the range of applications. So even if you don't think it's interesting to look at evil human users, think of this case. So suppose you develop an algorithm or let's say you develop a data structure and you need to assume an oblivious adversary. If you want to use that as a black box inside an algorithm, have an algorithm to solve maybe a static graph problem using your data structure for a static graph problem, then that algorithm will query your data structure, and based on that it will do some updates. And even if that algorithm has nothing to do with an evil user, just the way it works might actually destroy your analysis. It might still be it's still an adaptive adversary. So if you assume an oblivious adversary, then you cannot just use your data structure as a black box inside other algorithms. You need to somehow give a case-by-case analysis and see, does it actually work for this algorithm? Is this algorithm a bad adversary or not? So there are two ways to allow an adversary to be adaptive. Either you develop a deterministic algorithm, then there's no random bits, or you develop a randomized algorithm and then you somehow prove that it doesn't reveal information or enough information about the random bits. And for this result here against an adaptive adversary, we are actually not hiding the random bits completely from the user. So the user will at some point potentially learn something about the random bits, but as soon as that happens, we have time to choose new random bits. That's basically we do in analysis. We now have, when the user has learned, once the data structure has revealed some information about the random bits, we can show that then the data structure can afford to choose new random bits, and then the user cannot use that information for anything. Okay, so it's still not one, but I actually don't have more to say, but I was wondering if you had some questions for these 3 lectures. We could use the last minutes for that. If there's anything you want to ask or comments. Maybe there was something from yesterday's lecture, because that was maybe the most, I guess it was the most difficult one. You can also come up in a moment and ask me if you want to do it offline, but no questions?
So you're saying that with these all pairs shortest paths, there is no problem with adaptive adversary. Is that correct? Like
so for the
because it seems to me like all pairs shortest paths, when you delete vertices as we did, they can simulate connectivity.
Mm-hmm.
And for connectivity, there was a problem with this adversary.
So why? So you're asking? So
that was amortized. Yes, I'm asking if yesterday's algorithm worked against adaptive adversary.
So the algorithm we saw yesterday, you can say it works against an adaptive adversary because there cannot be an adaptive adversary. There's nothing to adapt to, except the running time, which we can delay. Mm-hmm. Because the output in each step is the correct distance matrix, mm-hmm. except this is a Monte Carlo data structure, so there's a small probability that it outputs something incorrectly, and if that happens, then the user could learn something, but then you're okay anyway, because you basically it happens with low probabilities. Let's say that this way, you don't want to reveal anything to the user until the first time that you make a mistake as a data structure. And with polynomially small probability, there's an error. So in expectation, you can have a huge polynomial number of updates before the first mistake happens by the data structure, and until that point, let's say we only care about until that point, there's nothing in the output that reveals anything about the random bits, because it's a true distance matrix we output.
Yes.
Yeah, and for connectivity, so we saw a deterministic amortized one, right? Since it's deterministic, there's no problem with adaptive adversaries. There's nothing to screw up there. But we also saw this XOR trick, and that was a randomized data structure. And there it actually is really, this paper that gives this XOR trick. The largest part of the paper is actually showing that the user cannot screw up anything, because the problem is that they maintain a spanning forest, and they choose a reconnecting edge. They choose one that was sampled. Remember this sampling trick, that you sample so that there's, with high probability, in one version of your graph there's only one reconnecting edge when you delete a tree edge. Let me just erase this. So if you remember this XOR trick, you had your spanning tree here, and then let's say this edge was deleted. If there was exactly one tree edge crossing this cut, you could use the XOR trick to find it, right? In logarithmic time. But if there were more non-tree edges, that trick didn't work. But then what we did is we said, okay, we just sample, we have different versions of the graph, and each version we sample with a certain probability, and no matter what the number of edges is here, there's one version of the graph where with high probability exactly one edge is sampled. So that means that maybe you sampled this edge here in this version of the graph, and then this is a reconnect with. But now this update that you did to your spanning tree depends on random bits. So the structure of the spanning tree is not, of the spanning forest, is not independent of your random bits. And that's actually a difficult part of the paper, to show that the user cannot screw up anything, basically. And even if you don't worry about the user, the algorithm itself might work against itself in some way, because the updates are depending on the random bits. But for connectivity, if you have a worst case structure, the output doesn't reveal any information about the random bits. Like, two vertices are connected or they're not, so if the algorithm gives the correct answer, there's no information revealed. Any other questions, comments? Still have 9 more minutes. No? So I guess we will stop a bit early. Thank you.